all of these things become obvious, and we'll again see why. So understanding the underlying linear structure of these problems allows you to identify what's important and what's not. What things are just can be handled with the general framework, what things cannot. So it gives you that extra power, that extra insight into a problem. And that's why you want to understand this. Okay? So without further ado, let's talk about what linear programming is. And for some reason, until I get an HDMI cable, because they've changed the projectors, I'm limited to this much viewport area, as you can see on my tablet. So I'm going to have to flip pages more quickly than I would like to because of the real estate. But again, the notes are linked on the Canvas page, so you have access to that as well. So don't worry if things seem to be going on flipping pages too quickly. Just tell me to go back. So what is linear programming? Like I said, it has nothing to do with programming, but it is definitely linear. And the typical form of a linear program is something like this. We have some kind of, so we have a bunch of variables. So typically we'll have variables x1 through xn. These are variables. Okay. You can think of this as the unknowns for your problem. If your problem is flow, this could be the flow value, so on and so forth. We also have a cost function. So and the cost function, because the name is a linear cost function. So a linear cost function of a bunch of variables will look something like this. So you might have c1x1 plus c2x2 plus cnxn. Right? And because it has to be in this form because we're talking about linear programming. That's the linear function. And you typically want to optimize this function, and for now we'll say we want to maximize this function. Okay. We'll assume that all the variables are greater than or equal to 0. So it turns out this is not a big problem, but let's just assume this is true for now. And of course, if you want to do this is trivial to the point of being nonsensical. You just make all the variables as, you figure out which coefficients are positive, make those variables as large as possible, figure out which coefficients are negative, and make those variables 0, and you're done. You make this thing infinitely large. As long as there's even one positive coefficient, this thing will be infinitely large. And if they're all negative, then you can make it 0. But that's not interesting. That's kind of a boring problem. What's interesting is that you have constraints. You have constraints on where the variables can be, or what values they can take. And these constraints are usually expressed as some kind of inequality. So for example, I might say that yes, I have these variables, I want to maximize this, but I want to make sure that a1, 1x1 plus a1, 2x2 plus a1n xn is less than or equal to b1. The reason for the subscripts will become clear in a second. But again, this is a linear constraint on the variables. So this automatically prevents me from making the variables arbitrarily large, because maybe in this particular inequality, if I make the variables arbitrarily large, this inequality will be violated. My a1, x1, a2, x2, so on will become huge. It will be much bigger than b1, and this is not allowed. And I could have any number of constraints of this kind. So if you assemble all this together, and it's convenient to put this in a kind of compact notation. Now, unfortunately, I'll have to skip to the next page because of my real estate problem. So let me sort of mark off here. If you assemble these all into a single package, what you're saying is that think of the C as a vector, think of X as a vector. So what we know how to write, what is C1x1 plus C2x2? We can write this as what is called an inner product notation. So C dot X is equal to sigma over I, Cixi. It's like taking the dot product of two vectors. Okay? So we can write our linear program in this form. Maximize C dot X such that, so I'm going to put a bunch of constraints here. So first of all, we said X should be less than or equal to 0. And again, this is an interesting constraint. I'm not saying Xi equal to 0, I'm just saying X greater than or equal to 0. We should interpret this as saying is that X is a vector, the zeros are also a vector, and coordinate by coordinate that inequality has to be true. So this is like saying x1 is greater than 0, x2 is greater than 0, x3 is greater than 0 all at the same time. Just a compact way of saying this. And in addition to that, we will have what is basically going to be a matrix constraint. And again, you should think of this as, oh well, a11 x1 plus a12 x2 and so on is less equal to b1 and so on and so on and so on and so on. You could have m of these constraints. So a could be, a is an m cross n matrix. Why m cross n? Well, you have m constraints and you have n variables. In different notation, you may have d variables and n constraints and get variables. Let's just stick with this one. This is called a linear program. In other words, a problem where you need to solve that, find the maximum value of c times c dot x under these constraints is called a linear program. Any questions? Yes.
So, by the way, so the first constraint into the second.
Pardon me?
The first constraint is a special case of the second one?
Yes, it's just nicer to write it out because usually those first constraints, they don't affect your dual in the same way. And you will see what that means. I mean, there's a reason why it's more convenient to separate out constraints like x greater than equal to 0 and not put them into the matrix. But yes, you could. Any other questions about this? So when someone says I have a linear programming problem, they mean they want to solve that. Maximize c dot x subject to these constraints. Yeah.
Let's say someone were lazy and if they have a problem without constraints but everything else is the same, can we still apply linear programming solutions to that problem?
You can, but like I said, it's much easier. If you drop the ax less than equal to b constraint and your x's are constrained, then your answer is either infinity or 0. So it's not well defined. And we'll see why in a bit. Once there's a certain geometric way of understanding what this is doing. And once we talk about that, you will see why it doesn't make sense if you don't have constraints. Okay. Now, this is what is called the canonical form for a linear program. You want to maximize a function subject to ax less than equal to b and x is greater than equal to 0. You might say, well, what if I have greater than equal to constraints? What if I have equality constraints? What happens to that? How do I incorporate that? The answer is it doesn't matter. And here's one quick thing about this. Suppose I have a constraint that says that, again, and I'm going to write this in short form because a dot x is greater than equal to b. Right? So you can think of this as one row of that matrix constraint. I have a single row A, and I have a single element B, and I want a dot x to be greater than equal to b. Can you see how to easily convert this into the canonical form? How would you do that? How do you take something that's greater than equal to something else and convert it to the form you want, where something is less than equal to something else? Sorry?
You turn your A into a negative A and transpose it, and there's your matrix.
I don't know what you need to transpose. I guess you just mean
Well, because you're doing a dot product there, right?
Yeah.
So dot product in matrix notation is A transpose X, right?
Oh yeah, sure. What you're saying is just replace A by minus A.
Yeah.
That's not enough. You need one more thing. It's a small thing. You need one more thing. You need to put B minus B. You multiply both sides by minus 1. That flips the inequality around. Right? When you multiply both sides of an inequality by minus 1, it flips the order of the inequality. So this is equivalent to right? So any inequality that is greater than inequality can be converted to a less inequality very easily, and then you can just stack this up in your matrix. So that's not a problem. Suppose you have an inequality of the form this. Now what do you do? How do you convert this into canonical form? Yeah?
Just put that as two constraints.
Which are? Thank you. So if you want to express an equality constraint, you can express it as two constraints. And we already know how to fix the second one. So we're back to square one. So that's not problematic. Suppose you want to minimize instead of maximizing. Then what do you do? Suppose your problem involved a minimization. Now what do you do here? Can you fix this one to put this canonical form? Sorry? Negate the c? Exactly. Because minimizing c dot x will be the same as maximizing minus c dot x. This is the beauty of linear operations. There are all kinds of tricks you can play by just multiplying this by minus 1, which doesn't change anything. So whether you have equality constraints, greater than equal to constraints, less than equal to constraints, whether you have minimization or maximization, it does not matter. You can always put this in a canonical form, as long as you have linear things. That's the point. Okay? So if you take a problem and you modify it in some way, as long as you have a whole bunch of constraints of this kind that are linear, you can get to the canonical form. And the canonical form is handy for certain kind of things later on. Okay? So that hopefully convinces you that this is a very flexible framework. It's not very specialized, it's actually very, very good. Okay? Alright. But does admit nonlinear constraints of low degree and then lift it up high enough that this all kind of works. If any of you have ever heard of kernel methods in machine learning, that's an example of taking this thing and lifting it to an infinite dimensional space. Right? And then that's where things become flat. But again, let me continue with the geometric interpretation of what's going on, and then this will all make a lot more sense. Okay? But yes, this is exactly what people try to do. Okay. So, what does this all mean? So I have some kind of plane. I'm going to draw the plane somewhere here. Okay? So this is the x1 dimension, this is the x2 dimension. Okay? And I'm looking for some solution that lies, remember, since they're both greater than or equal to 0, I'm looking for some solution that lies in this region here. Right? Okay. Let us look at what a constraint may look like. So we said a constraint is in the form a1 times x1 plus a2 times x2 is less than or equal to b. Right? So let's write this out. So let's say, I don't know, x1 plus x2, let's keep it simple, is less than or equal to 1. Okay? Alright. What region of that first quadrant does this inequality capture? Well, the way to think about this is that let's replace that inequality by equality. If we say x1 plus x2 is equal to 1, that's a line, right? It's a line. We're used to thinking of these lines. And what does that line look like? Well, I chose it because I know what the line looks like. It looks like this. Right? This is 1, 0 here. This is 0, 1 here. And it's a straight line between them. And it's not hard to see that if you're looking at the constraint x1 plus x2 is less than or equal to 1, it's going to be everything on one side of this line. Okay. Now, which side of the line? That depends. In this particular case, it should be not hard to check that, well, let's look at the point 0, 0. 0 plus 0 is less than or equal to 1, and this is on this side of the line, so it means we're talking about everything on this side. But we also said x1 plus x2 is more than 0, so we're looking at this region here. Right? So the inequality we just wrote down is basically saying, I want all your possible answers to be on one side of this line. Alright, let's write down another inequality. Someone give me an inequality. Not too hard constant, so I can actually draw it. Any thoughts? Something involving x1, x2.
x1 less than 1 half.
Sorry?
x1 less than 1 half.
Oh, let's make it a little bit harder. Let's combine those two. Something plus something. Anyone? What do you want? Just make it easier so I can actually write a draw. Okay. Come on, it's not that hard to do. Anything? Anyone?
2x1 plus x2 is less than or equal to 1.
Thank you. Okay, fine. All right. So if we had to draw this, where will it be? So let's look at the line. 2x1 plus x2 is equal to 1. Where will this be? So 2x1 plus x2 is equal to 1 then this line will pass through 1/3, 1/3, right? Let's say x2 is 0, then x1 is equal to half. So it's here. Let's say x1 is 0, then x2 is equal to 1. So it's kind of this line here. Oh no. Okay. This is my line, and this is the region here. Okay? So this is unfortunately not the most interesting of lines because it's just a subset of the previous one. But nevertheless, by adding this second constraint, I have constrained the region where my points can lie to an even smaller region, the intersection of these two feasible regions. So now I keep adding constraints like this. Every time I add one more constraint, I intersect that free region with whatever I have so far. So the region is getting smaller and smaller and smaller and smaller. Right? So in general, what's going to happen is that what I'm going to end up with if I draw this thing out, let me draw this here, I'm going to end up with some kind of region that looks like this. This is going to be my screen. And if I'm lucky, it'll be closed. It may not always be closed, but this is going to look like this. So every set of constraints corresponds to some kind of polygon. The polygon could be closed, it could be open. So for example, a different polygon could be something that looks like this. So this line goes out that way, this line goes out this way, just so that everything goes out that way. So it could open up completely, or it could be closed. It depends on the inequalities you have. But a set of inequalities you should think of geometrically as some kind of polyhedral region. Of course, if I have 3 variables instead of 2, now you can imagine this, I don't have lines anymore. What do I have? I have planes. Right? I should have brought my little polyhedral model with me. So you have planes cutting like this, so you have some kind of polyhedral shape, which again could be open. In general, in n dimensions, if you have n variables, you have some kind of n-dimensional polyhedral shape. When I say polyhedral, I mean that it's bounded by these flat things, linear things. Okay? Yes?
If it's open-ended like that, then you the solution infinite.
Yes. Well, depends. It depends on one more thing, and we'll get to that. We're not quite done with this. It may not be. Okay, so the geometric interpretation of the constraints that constrain your variable are this kind of polyhedral structure. So the next question you have to ask yourself is, what is the interpretation of this maximize c dot x? So does it make sense? Can I go on here, or is this clear? Okay. So what does c dot x look like? So now that we've agreed that the constraints describing your variables look like a polyhedral region, let me just draw one. So I have some kind of polyhedral region. And let's say for now it's closed. We'll look at what happens next when it's open. But we don't know what it looks like. It looks like this. Right? And of course you should imagine these things actually, they're all lines. This is just the intersection of lines. Right? We're just looking at different sides of each inequality here. Right? What does c dot x look like? So again, now if you think about what c dot x is, suppose I say, okay, c dot x equal to 5 or c dot x equal to 6. This is also the equation of a line, right? So for example, if I say that, so I want to maximize, let's say I want to maximize, again, x1 plus x2. Okay? And I'll write this as, this is going to be important, I'm going to write this as 1 dot x1 plus 1 dot x2, or as 1 comma 1 dot x1 comma x2. Right? I've just rewritten the same expression, but I want to make this point. What is the line? Suppose I want to maximize x1 plus x2. Let's say the maximum value is 1. Okay. What are all the possible answers for x1 plus x2 is equal to 1 in this region? So let's say my x-axis was, my coordinate frame was here. Okay. In the feasible region, where would my x1 plus x2 equal to 1 lie? So we draw this before, it might look something like this. I don't have the exact thing here, but it might look something like this. Right? This is the line x1 plus x2 is equal to 1. So any points in this region here are valid solutions to the problem where x2 plus x2 is equal to 1. So the value of the solution will be 1 for those points. What about x1 plus x2 is equal to 2? What would that line look like? Yeah, you were moving your hand. I think you had the right answer. You want to? You shifted, right? So you shifted parallel to itself because the slope has not changed. It might look something like this. Well, it won't look like that. It'll look like this. And these are all the points where x1 plus x2 is equal to 2. Now, if I'm maximizing, looking at this shape and looking at our problem. Do you think that's maximum value? 2? Do you think we'll do better? Could we do better? Could we increase the value of the optimal solution? Do you think x1 plus x2 equal to 2 is the right answer if this is the feasible region of x's? What do you all think? No? Why not?
Because there's still some region that upon this.
Pardon me?
There's still some value
Region space to move into? So how far could you go?
the top of the.
So we could keep going. We could keep drawing lines here, but we can go further. We could go here. We could still go further. Where do we stop? We stop here, right? Right at the tip. This is the optimal solution to the problem. Okay, that's fine. But let me ask you one more thing. We know all these lines are parallel to each other, right? If we had to draw kind of their direction, we could imagine a little arrow that's sitting on top of this line perpendicular to it, right? It would look something like this. Right? It's kind of pushing us in that general direction. Right? It's a little vector. What is that vector? If our lines were x1 plus x2 equal to constant, what is that vector? Sorry?
1, 1.
1, 1. So we said that the geometric interpretation of the constraints was that you have this kind of polyhedral shape of feasible region. The geometric interpretation of the maximization is a direction. That C is your direction. What it's saying is, take this polytope, go in the direction given to you by C, and see how far you can get till you leave the shape. And that point where you leave the shape right there, the tip, that's your answer. That's going to be the largest value you can get. And in fact, for any linear programming problem, one second, for any linear programming problem, if it's closed, your optimal solution is going to be at a vertex. And it's not hard to see why. Suppose my answer was at some line. Suppose it turns out that one boundary of the polytope was parallel to that line. Then any of those two endpoints will also be a solution. In fact, everything along will be a solution. So without loss of generality, a vertex of that polytope is the answer to your linear programming problem. Yes?
So is it 1, 1 because the coordinate?
Sorry?
Is it the coordinate of the number or I didn't understand how it's 1, 1.
How, what is one? The direction?
Yeah.
Because, how do I say this? It's 1, 1 because the lines are of the form x1 plus x2 equal to constant. Right? what you can show is that basically the normal, the perpendicular to that such a line, is in fact the one point. Because it's essentially, so you can say, okay, if you write it down, what is the set of all points such that 1 dot x, x2, x1, x2 is a constant? It's a line whose normal is 1, 1. That's in fact the way to define a line. Another way to define a line is to say, I'll give you the normal to the line, and then look at everything. This is actually better because in higher dimensions, it's to describe a plane, it's easy to say, okay, what's a normal to the plane? So I have some kind of plane. I have the normal to the plane, which is a single vector. So look at all points that are perpendicular to this normal. That's this whole plane. So that's a more general way to describe a higher dimensional hyperplane in n dimensions. Any other questions? So yeah.
So you could have multiple valid answers if there was like concaves.
If it was flat. So you could have multiple valid answers if, for example, you were kind of if your direction was normal to this shape, for example. Then you have all these would be
What
valid.
if there were like two other lines that were like coming in, so that like they're just like the endpoints of that line were valid?
I'm not sure I follow. So let me label these things. So maybe
He's saying that it's a concave shape instead of a convex shape, but in linear programming you can't have a concave shape.
yeah, you can't have because it has to be flat.
Okay.
You can't have curves
Okay.
because your expressions for the boundaries are always linear functions.
Oh, okay.
So I think you were
Oh, that's right. Okay.
right. So you're not gonna have like this kind of thing or that kind of thing in the boundary. It's always going to be flat.
Okay.
It's going to be in particular a polyhedron. A polyhedron is a collection of flat facets.
Well, I wasn't saying flat, but like, yeah, pointed in, but yeah. I guess,
But that's also
I
the
guess
same
that
thing.
would-
That's not
yeah.
flat. Yeah, it's pointed in. Right.
Yeah.
Right.
Okay.
Right. So concave is also this.
Yeah.
Yeah. Okay? So now we have a clear geometric intuition of what a linear programming problem is. It's saying, I give you a polytope in n dimensions, and I give you a direction. Go inside the polytope all the way to the end and see what point you hit. And again, you can prove that you'll always end up with a vertex, or that a vertex will always give you the best solution. There may be others, but a vertex will always be one. Okay? Which also means something else, right? If I want to find that point, suppose I took my entire polytope and turned it around. That means turn the polytope and turn the direction. Will I change my solution? No. It's the same thing, I just changed my coordinate frame. So without loss of generality, you can also assume that the whole problem of linear programming is find the lowest point in some polygon. So what I'm saying is, and let me write this down. So without loss of generality, by rotation, linear programming is the same as find lowest point in a polygon. And this starts becoming a lot like the optimizations you've heard of. You've probably heard of gradient descent, you've heard of hill climbing and hill descent and things like that, where you're kind of going down the landscape. That's kind of what's happening here. Right? Without loss of generality, you can pretend that you're basically going downhill. You can find the bottom point, some kind of basin, which is a polygon basin. That's what linear programming is. And it turns out pretty much, many of the optimization problems we will ever look at can be visualized out. Trying to find the bottom point or some kind of polygon basin. Okay? Yeah.
What do you mean by lowest?
Good. What is lowest point? I fix one of my variables as z, lowest value. So instead of saying maximize c times x, I can say maximize the z coordinate.
Okay, so you're maximizing the one, or minimizing the one.
One variable, because essentially by rotation, I can make my c vector look like a single vector with a single one. Because any vector, point this way, I can turn it, so it's pointing down.
So why would you want to, for example, find the lowest point along all axes?
I could, but that's multiple different optimizations that I'm doing. Linear programming is finding one such optimization, one such minimum. You can, there are many, each of those instances you're asking for will be a different linear programming problem. You could imagine trying to solve them all separately. Sure. But they're not, they're different problems. They're all individual problems.
Well, rotating it, you could rotate it to like, you could rotate this to like, have that line be on the x-axis
Yes,
or the y-axis, and those would still be the same problem.
Yes.
Yeah.
So you can do any one of them.
Yeah.
Yeah. That's what I'm saying, just think of the lowest point, because like the same. And by the way, this tells you why minimization and maximization don't matter. What does minimization and maximization correspond to in this intuition? It's basically saying either I go forward or I go backward, right? But if I go forward with this direction, I could go backwards with the direction reversed. It's the same problem. But the direction being reversed, that's multiplied by -1. That's why it doesn't matter whether you minimize or maximize. What does greater than or equal to, less than equal to matter? Which side of the hyperplane you're on. You can just flip the sign, right? Decide which side you want to be on. That's why that doesn't matter. And that's why I'm saying the geometric intuition of the polytope tells you why these things that might look like they matter in the algebraic expression of the linear program don't actually matter. Because geometrically speaking, it's all the same thing. It's just that which coordinates you're using to describe it change, but the fundamental object you're trying to work with is the same object. It's the same polytope. Okay? All right. Any questions? Any other questions? Okay. What I want to do is give you a few examples of what a linear. Well, before I do that, let me do one thing, and we'll take a short break, and I'll use some examples. But now we go back to the question of what happens when might you get an infinite solution to your linear program? When might you get no solution to the linear program? So let's talk about that for a second. Okay. And we'll take a quick. Okay. So now that we have this intuition of a polytope and a direction, let me show you how things could go wrong. So here's one way in which things could go wrong. The easiest way is which there is no polytope. Can that happen? Suppose I have a problem. I'm going to draw again things in the plane again. Right. So suppose I have one line. This is one constraint which I can describe as a line, and I want everything to be on this side of it. I have another constraint, and I want everything to be on this side of it. So far, what's our feasible region? Our feasible region is everything on this side of this first line, everything on this side of the second line, which will be basically this region right here. Yes? Suppose I have a third constraint here, and I want everything to be above it. Can I solve this problem? No. This has no solution. So the polytope is empty. If this happens, you can't find any answer. Your set of constraints are infeasible. There is no way to satisfy them. So that's one problem that can happen. The other problem that can happen is that you have an infinite solution. So in one way, at least you have one, but it's infinite. Why would that happen? Let's again draw our graph here. Suppose our polytope, and I'm going to draw this, the boundary of the polytope, looks like this. Right? And that's it. I stop. I don't have any other constraints. So basically, I want to be inside, I want to be inside, I want to be inside. These are my directions. So everything in here is valid. Okay? And let's say the direction I'm looking for is this direction here. In other words, that vector is the C vector. What's going to happen? If I want to maximize, I'll just keep going all the way to infinity. But just because this polytope is open does not mean that I can never get a valid solution. Suppose, for example, my direction was this one. Then what's my best solution? Well, my best solution is going to be this vertex right here. Okay. So it's a combination of the polytope shape and the function you're trying to, the vector you're trying to optimize along that decides whether you'll have a infinite solution or you'll have an actual finite solution. But if the polytope itself is empty, then of course there's no hope for you. You're not going to find it. Right? So this is infeasible. This linear program is infeasible. This linear program is unbounded. Right, in this case here. Okay? So your program can be bounded, can be unbounded, it can be infeasible. All these things could happen. Depends on the problem, depends on the constraint you have. Okay? On that note, let's take a short break, 5 minutes, and then we'll come back to the some examples. How's
So the social network paper references a hill climbing algorithm.
Yeah, come on.
Yeah. So then it's holding
So gradient descent is a particular it's almost looks like
it's really complicated.
See, hill climbing method basically says always should but you may not go on. Usually gradient descent are essential. The gradient descent the law thing you have one is things like and by so now we don't issue before we get those we found out that many years ago same thing with reader all the early ones but in parallel something happening. So a lot of results generate The questions are mostly linked to the notes. So make sure you download the PDF folder. Make sure you download the lecture notes in there. So keep them offline. So that's what I would say. You're not going to videos are not going to you have the right access. The assignments are linked. try to keep it so if you're using the problem, you shouldn't apply I don't, yeah, so I don't know the order of problems. Again, there's a level of difficulty involved. Well, all I say is don't be driven by the it's just because there are five questions. So 100 divided by 5 is 20. It doesn't mean these are so hard. Yeah, I don't think we should do that. That's not right. And yeah, so this is not
So like 3D would be yeah. Could you do like just a line
I am reading you want to express it in street office, they have to be
like what you're maximizing. You only had a line.
Well, you think of that sweet, like you're sweet in the process. You stop. That thing you sweet. I really only are playing because the vector is the thing.
You have the same one.
No.
Okay, yeah.
The vector is the thing. Vector one All right, let's continue. So there were some questions which I remind me after notes. Next week, Tuesday, I will actually not, there will be no class, I will not be around. Unfortunately, I have to travel and get myself worked out. So there will be no class on Tuesday. I will do some more as well. You're off on Tuesday. Secondly, a question came up about the assignment. The fact that the questions are 20 points is a consequence of the Pigeonhole principle. Namely, there are 5 questions and 100 points. It does not mean these are 4 times as hard as the 5-point questions you had in the No, they're not. They might be twice as hard. They're not 4 times as hard. Okay? So don't be afraid. Just I didn't want to give you like a gazillion questions. Okay. All right. So those are 2 things. Again, I'll post a note about not being here next Friday. Also want to remind you again. Tomorrow we have the hackathon. It's 3 to 12, right? Yes. Okay. 3 to 12, and we know the room number. The room locations in the web.
Yeah, it is. Yeah.
In the gallery. So they come to the So they come to the Canonical Gallery. You'll be here. So starts at 3, right? Or 3 o'clock.
Yes.
Okay. And also there is the invited lecture at 10 o'clock in web 12:30. It's upstairs tomorrow morning at 10 o'clock. So do attend it. All right. So let's continue with some examples. Okay. So the reason why we study linear programming is that it is a very, very flexible and versatile framework to express problems. Otherwise, we'll be wasting our time. And I want to convince you of that by first showing you some examples of problems that you're familiar with, to show you how to put them in this framework. Okay? So let's look at a first problem. Shortest box. So I give a graph, and I have S and T, and I want to find the shortest path from S to T. Okay? Here's how you could do it. So what I want to do is maximize VP. So I'm going to have one variable called di for each vertex. So dt is the variable for the vertex t. So I want to maximize this dt such that ds is equal to 0. Okay, all di's are greater than or equal to 0. And for any edge uv, so there's a whole bunch of constraints, right? And all the edges have weights on them. That's why we're trying to compute distances. This is a linear program. Why? You are maximizing 1 times dt, which is an appropriate inner product. It's a one variable, we don't care, that's fine. Think of it like it's like a vector of a bunch of zeros, just 1, 1 for dt. That is dot the variable, so the vector of all variables. You have constraints, ds equal to 0. As we said, equality constraints can be handled within our framework. And you have this inequality constraint, which is more standard. And you can think of this as 1 times du plus minus 1 times dv for all uv. So since I said for all uv, think of your matrix as a whole bunch of rows. Right? I said there are m constraints, in this case there will be e constraints, 1 for each edge in the graph. And it's not completely obvious why this should be a linear program that actually gets you a shortest path from S to T. In fact, it's weird because you're maximizing, right? You're minimizing. But then you want to find the shortest path. Why are you maximizing? But if you think of what's going on here, what's happening is this. What you're doing is computing labels for each vertex. And I didn't choose that B by accident. What you're really saying is find me the distance, shortest path distance, from S to every vertex. And in particular, I want to find T. But ds is equal to 0 because the distance to yourself is 0. And what is this constraint telling you? This constraint is saying is that if you're going along some path and you go from, V to U, let's say, in this case the way I've written it, there's no reason why the distance to U should be more than the distance to V plus WUV by triangular inequality. Right? So if you think of this as a diagram here, so let's say I have this edge, V and U, and its length is WUV, right? I have some shortest path from S to V. I have some shortest path from S to U. If this is the distance from S to V, which should be dV, and this is the distance from S to U, which should be du, there's no way du can be more than dV plus the distance, right? This doesn't make any sense. Because our triangle inequality, I can always do that. And it turns out this set of inequalities is enough that if you solve this linear program, you have solved the shortest path problem. And you can improve it. This is again a weird way of writing, but I'll show you another way of writing it that's a little less weird. The point that I'm trying to make is that you can take a problem that you're familiar with and put it into this framework. Now, I'm not recommending that you actually solve shortest paths by doing this, because you can solve shortest paths a lot more easily than doing this. But the linear programming framework allows you to express things like shortest paths. There is another way you can express this. So the funny thing about linear programming is that given the problem you want to solve, there isn't like a unique linear program for that problem. You can express that problem in terms of linear programming in many different ways. And in fact, some of the cleverness in algorithm design comes to find the right way to express a problem as a set of constraints. Okay. For example, in this case, instead of expressing in terms of this maximization of this vertex, you can do a minimization where you now say, instead of having a variable for each vertex, I have a variable for each edge. Okay? So what I'm going to do here is say, let me go to the next page. So let x uv, we'll think of it as being equal to 1 if uv is chosen for the shortest path. From S to T. Okay? So we want to get a bunch of variables, we'll encode them so that we're saying, okay, we want this variable to be 1 to signal I'm picking up this edge to get the path from S to T. Okay? In that case, what would be the length of this path? It would be equal to So I want to minimize the length of the path, which would be equal to sigma WUV times XUV over all edges in the graph. Because my intention is to make sure that I only set a value for an edge variable to be 1 if I pick it for the shortest path from S to T. Even if I sum up over all the edges of the graph, this is going to work because everything else will be 0. The question is how I'm going to force that to happen. I'm going to force it to happen by setting up some constraints. What are my constraints? The constraints I want to have one edge coming out of the source, right? So in other words, if you look at all the edges coming out of the source and you sum them up, so you sum up all for over all W X SW, where SW is actually an edge, so SW belongs to E, right? Should be equal to 1. So all the edges of the source should have value 1. All the edges out of the sink, that are adjacent to the sink, should be equal to 1. Right? And for every other vertex, the sum should be 0. Well, sum should be so let me pretend the graph is directed. It'll be easier to say this. So then, so hold on. Let me draw out something. It'll be it's a bit easier to explain what I want to do if I draw things out. So in other words, sum of S comma W belonging to E X S W minus sum V comma S belonging to E X V S is equal to 1. And for T, you do the other way around. So sum of T comma W X T W minus sum over V comma T X V T is equal to minus 1. And then for everything else, for all V not equal to S comma T, sigma U comma V X U V minus sigma V comma W X V W is equal to 0. Okay? And all these x's are greater than equal to 0. This is also a linear program. All the constraints are linear, the cost function is linear, and you can always massage things in the right canonical form. Right? This is a different linear program that will give you the same answer. Of course, there's one catch here, that these x's may not be 1. They might have fractional values. It turns out that actually won't happen. You can always find values of x that are 1 or 0, but why that's true is a little bit more tricky. I'm not going to get into that right now. Needless to say, you can write a linear program that captures these constraints and captures what you want. So, as a normal problem, shortest paths can be expressed as a linear program, in fact, in 2 different ways. Okay? And then it should come as no surprise to you now that something like max flow can be expressed as a linear program. When you think about it, when I do maximizing the flow, what is the flow value? It's a sum of all the flow coming out of the source minus the sum of all the flow going into the source. Kind of looks like this a little bit. Without the weights. So let's write down what a flow formulation would look like. So is this clear, by the way, the second linear program for shortest paths, how it works? Basically what I'm saying is I want to encode a situation where each edge is either picked or not picked. If it's picked, it's 1. If it's not picked, it's 0. I want every vertex in the graph to either have 0 edges going through it or 1 coming in, 1 coming out. Right? And I want the source to have 1 and I want the sink to have 1 going in. That basically encodes the idea of the path. And I just want to minimize the length of the path. So all these constraints say, give me a valid path. The optimization says, give me a valid path of shortest length. That's a modular way of thinking about this. So in fact, if you have another problem on paths, you could take the same polytope, just write a different cost function. If you want to say find longest path, you apply this by maximum. And you'll find, you won't find the longest path, well, that's another story, why you won't find the longest path. But you can write this that way. The polytope gives you the constraints, and the optimization tells you what you want to do. Okay? Flows. How do we write this in terms of flows? So why don't you all think about that for a second. I'll give you a few minutes. Think about how you would express max flow as a linear program. In order to do that, you have to say, what are my variables? What am I trying to, can I write my variables in such a way that the thing I'm optimizing is a linear function of the variables? And what are my constraints? Can I write them as linear functions? These three things you think. Variables, constraints, cost function as linear function of variables, constraints as linear functions of variables. Okay, think for a few minutes. You can talk amongst yourself. All right. So, question one. What are the variables for my linear program? What do you think they should be? Yes?
Just one for each edge.
You want one variable for each edge. What is that variable going to encode?
Like how much flow is coming through that.
Okay, so one proposal here is to have one variable per edge, where the variable will capture the amount of flow you want to place on that edge. Does everyone think that, has everyone also more or less come to the same idea, or does everyone have a different way of thinking about encoding the variables? Is there any other suggestion for how to encode the variables, or is everyone sort of settled on this particular one? Remember, there are many different ways you could express a linear program. So there's no one right way to do it. This is, clearly one of the more natural ways, but it's not the only way. Okay, so we'll go with that. So we want one variable. So one variable per edge, and the intention is that you want it to capture flow. So we'll just call it, we'll call it FUV. Okay. All right. So that's variable. Can we write down the thing we want to optimize as a linear function of these variables? How would we do that? Anyone else? Any thoughts? If these are variables, what would be a linear function of these variables that would?
So you can make C be the vector of edges coming outwards.
You mean the incidence like the ones and zeros kind of thing? So don't worry about what C is. We can figure out what C is later. Just give me an expression That's a linear function of the variable. That's good enough.
Right, so you're trying to optimize the amount of flow that goes out of the source.
Right, so you want to say, you want to maximize the sum over all edges of the form S comma V, F, S, V. Of course, you have to subtract the flow going into the source, because you want the net flow going out of the source, minus the sum over all U comma S, F, U, S. Is this a linear function of my variables?
Yes.
Yes, because I'm only adding multiple. It's fine. So far we're okay. We've got variables, we've got a linear function of variables. What are the constraints? Can we express the constraints also as linear function of the variables? And again, don't worry about less than equal to, greater than equal to, we know we can fix all these things. So tell me in any form you want. Give me one constraint that we want the flow values to satisfy.
They all have to be positive or non-negative.
Yes, okay, that's one constraint. So all flow values are greater than equal to 0. What else? Any other constraint? What do we know about flow? What properties does flow have?
We want to make sure that the number coming in is the same as the ones coming out of each vertex.
For every vertex that's not source or sink.
Yeah.
Okay, so how do we write that? We say, okay, what's the total flow coming into a vertex? That's sum over all U comma V, F, U, V should be equal to sum over all V comma W, F, V, W for all V. So there's one constraint for each vertex, right? So you're stacking them up in your matrix. Okay, what else do we have? Do we have any other constraints that we need? We're forgetting one very important constraint. Yes?
For all F, U, V, it's less than the capacity.
Thank you. So we have a capacity on every edge, and we want F, U, V less than equal to C, U, V, which is a constant, for all U comma V in the edge. Right? So we have capacity constraints and we have conservation constraints. So we should say for all V not equal to S comma T. Okay. Are there any other constraints we need here? Is this enough? Yes?
Well, the flow going out of the source and going into the sink has to be the same also. So
Do you need to put that as a constraint? Because the flow going out of the source cannot get lost anywhere because for every other vertex, it will end up being the same. So you could write it. There's nothing wrong in writing it. It will turn out that you won't need it. So it will be one of those situations where in your polytope, you will have one more constraint, but the constraint will not change your problem anyway. So that's the equivalent of adding it. So it won't hurt you, but sometimes it's better to have fewer constraints involved. So this is it. We now have a linear program for solving flow. And once you look at it this way, you realize why all those little transformations we did in the flow work. Because all they do is express other linear constraints. Oh, we want the flow to be at least something, right? Suppose a demand case. Well, we just write, oh, the flow UV should be greater than or equal to DUV. In the flow formulation, we had to work very hard to make sure that we did all the jiggling and stuff like that to make it work. But the linear programming formulation is trivial. It's just one more constraint. It doesn't change the problem in any way at all. It's a different polytope, but fundamentally it's still a linear programming problem. And there's more to it as to why you can replace this convert this to a normal flow. There's a bit more subtlety in there. But what I'm saying is that once you think of this as a linear programming problem, these are just more constraints to add. They may not really change the problem fundamentally. They're still linear constraints. Okay? You can do the same thing for the min cut. You can actually write down an appropriate linear program to solve the min cut. And again, it's in the notes. It's very interesting to see how it's fun. Again, so just as a thought experiment, without writing it down, if you want to express min cut, what would your variables be? What do you want the variables to be if you try to find a min cut in your graph? Think of the decisions your algorithm is going to have to make. What is it deciding fundamentally? It's deciding to find a cut, right? What is a cut? What's a cut? It's a set of vertices. So how might you encode variables to pick a set of vertices? What might you do? Sorry? So, what's the variable? I want a variable to encode the act of picking a set of vertices, right? So, yes.
Try to do what we did before, where we say the x of u or uv is equal to 1 if we've chosen 0 otherwise.
Yeah, so x, so you treat one variable for each vertex. You want to make it 1 if you pick it. You want to make it 0 if you don't. Then the min cut will be some minimized sum of xv. And then you have a whole bunch of constraints you have to set up. So again, this is in the notes. You can take a look at it as a way of doing it. Yes.
So will the polytope be the same?
Good. What is the dimensionality of this polytope? In other words, how many variables are there in it? How many variables is this polytope? Number of edges, right? That's the dimension of the polytope. How many dimensions does that look like?
I guess number of vertices. So I guess I'll just have like the same vertex, or it'll like share the same common.
So it turns out that there's a notion of what is called duality, which we'll talk about next time, that allows you to transform a linear program into another linear program, so that the max of one is the min of the other. The reason why max flow and min cut are related is because they correspond to dual linear programs. So you have one polytope here, you have one polytope in a different dimensional space, and they just touch it. And that's what duality is. You'll see that. But that's why it doesn't have to be the same polytope. The shape of the polytope depends on the set of variables and the dimension of the variables. So before we leave, I want to say one thing. We said that a linear programming problem corresponds to finding a vertex of a polytope. Okay, so here's an algorithm, right? Given a polytope, compute the vertices and check the cost of each vertex. That's your answer. Why doesn't this solve every linear program? Well, maybe it does. It does solve a linear program. What's the problem with this? So in other words, I have a polytope. Think of it like a polygon. So you have a polygon, right? You can just, by intersections, you can compute all the vertices of the polygon. Check the value of the cost on each of these vertices. We know one of the vertices is going to be optimal solution. Just check them. What's going to go wrong, if at all?
You have unbounded situations.
That's one problem. Suppose it's bounded. The thing is, if you have n variables and you have n constraints, you could have something like n to the n possible vertices. It's hard to visualize, but what I'm saying is that if you have a three-dimensional polygon and you have n constraints, you could have n cubed variables, n cubed vertices. Well, 3 you can't, it's only n, but in 4 dimensions you could have n squared vertices, and in 6 dimensions you could have n cubed, and so on. The number of vertices is exponential in the dimension of the polygon. So you can't actually enumerate over all possible vertices. In fact, for a very long time, people thought that linear programming was an NP-hard problem. But it was in 1978 that Kachian first showed that there in fact was a polynomial time algorithm to solve linear programming, which was a big deal. In fact, the first book on NP-hardness stated linear programming is a big open question. Is it NP-hard or not? And in 78, it was shown that it's not NP-hard, and in 84, Karmaka gave another algorithm which was even more efficient for solving linear programming. But till then, the only algorithm we had was the algorithm called the simplex, which was developed in the 40s, which basically took your polytope and kind of walked down the vertices to find the lowest point. And that could take exponential time. There are examples where it takes exponential time. So no one knew for nearly 40 years whether you could do linear programming in polynomial time. Someone asked about the history of this problem. Notes are very nice history, but the idea of expressing a problem in this form goes back to the 30s in Russia as a kind of way to do optimization, sort of manage sort of production and supply, things like that. And again, in the 40s in the US, about the same time, there were similar developments happening. They were happening in parallel because no one knew what the other person was doing because of the iron curve. And at some point, we figured out all these things happen. People in economics were trying to figure out how to do linear programming. They didn't call it that, but they were trying to sort of figure out how to do it. So a lot of different areas were trying to get at this problem from different directions. And then Danzig, back in the 40s, came up with the simplex algorithm, which runs an exponential time. And then, it took 40 years to go into the algorithm. So this is a problem that's been studied for a long time. It's like the bedrock of all of optimization. You work in operations research, you do any kind of scheduling, any kind of work. Linear programming is your bread and butter. And it's cousins. So that's some of the perspective on this. Again, the notes are very good historical sense of what the history of this problem. And we will talk more next Thursday. Okay, not next.
And I think constraint should be